Ever find yourself using a website, one you really depend on, or maybe a service that's like always up and running, and you just wonder, how does it stay online no matter what happens?
It is kind of amazing, right?
Yeah.
What's the secret sauce behind that rock-solid reliability? What are they doing that makes them so resilient?
That's exactly what we're digging into today, the how-to of engineering a system that not only works when everything's perfect, but actually keeps chugging along even when things go wrong.
Right, because let's face it, in the real world, stuff happens. It's not a matter of if things will break, it's when.
So true. And to really get a handle on this, we've got this deep dive into a seriously cool project, a home lab that's been designed for maximum resilience. It's like almost on par with a small business setup.
I mean, this isn't just some out-of-the-box solution either. It's something that has evolved over time, adapting to meet the growing needs for redundancy, speed, and that all-important flexibility.
Yeah, this wasn't some overnight thing. This was a process of learning, experimenting, and refining.
And that's what makes it so valuable for us, right? Because it's a real-world example of how practical needs and a desire for dependability can lead to these really innovative solutions.
And the best part, it doesn't require some massive corporate budget. So it's definitely achievable for those of us who, maybe don't have unlimited resources.
Absolutely. So we're going to break down the journey of building this resilient lab, look at the specific hardware choices, the network design, and try to understand the key lessons that were learned along the way.
Think of it as getting a behind-the-scenes tour of how to build a robust system. It doesn't matter if it's for your home, a small office, or even just for learning. Our goal is to figure out the core principles that make this lab so resilient, and then, hopefully give our listeners some actionable insights they can apply to their own tech projects.
So let's start at the beginning. What was the initial spark that set this whole journey in motion? What was the starting point?
Okay, so picture this. A single Proxmox server connected to a single network switch. Pretty typical setup for a home lab, right?
Yeah, I mean, that's how a lot of us start. You dip your toes in, get a feel for things.
But then things change. You need more power, more flexibility. Maybe you're running more services or experimenting with new stuff. The demands grow.
And that's where things get interesting, because in this case, the goal shifted. It went from just having a functional lab to creating something with high availability. It's like minimizing downtime as much as possible.
And real-world resilience, the ability to bounce back from actual failures, not just those hypothetical, everything's perfect scenarios.
Right, because things break, hardware fails, connections drop. That's the reality.
And what's really interesting is that this evolution, this drive towards resilience, wasn't driven by some abstract theory. It was fueled by actual pain points, real frustrations that the creator experienced.
Yeah, that's where the rubber meets the road, right? It's one thing to read about best practices in theory. It's another to get bitten by a system that's not as robust as you thought it was.
Exactly. And the specific trigger, the thing that really pushed this project towards high availability, seems to have been the dreaded loss of quorum in the Proxmox cluster. Anyone who's dealt with clustered systems knows that losing quorum can be a nightmare.
Oh, tell me about it. You're locked out of the management interface. You can't access your systems. It's like the digital equivalent of losing your keys.
Exactly. So let's fast forward to the present day. The lab has come a long way from that single server and switch. What are we looking at now?
Okay, so hold on tight. The current setup includes 2 core network switches, 2 access switches, 4 Proxmox compute nodes, and not 1, but 2 dedicated pfSense hardware firewalls.
Wow. Talk about leveling up. It's clear that resilience is the name of the game here.
And the core design principle that runs through everything is this. Everything, and I mean everything, is wired to survive failure.
Okay, bold statement. How does that actually play out in practice?
Let's start with the network. Inside each Proxmox node, there are 3 network bonds, which are like combining multiple network connections into one super connection.
Okay, so it's not just about redundancy, it's about combining those connections for increased bandwidth too, right?
Exactly. So the first bond, let's call it bond 1, uses 2 10 gigabit SFP plus connections. These are like the high-speed lanes of the network. They're aggregated using LACP, which stands for Link Aggregation Control Protocol.
So if I'm getting this right, LACP basically takes 2 physical connections and makes them act like one big, fast pipe.
You got it. This increases the bandwidth and also introduces redundancy. If one of those 10 gigabit links goes down, maybe a cable gets damaged, the traffic can still flow over the other link.
So you don't lose connectivity or performance even if you have a hardware issue. That's pretty slick.
Then there's Bond 2, which works similarly but uses two 1 gigabit RJ45 connections. These are your standard Ethernet ports. It's also configured with LACP, but it connects to a completely different 48-port switch.
So not only do you have redundancy at the cable level, but you've got it at the switch level too. If one switch goes down, there's another path available.
That's the idea. Eliminate single points of failure wherever you can.
But then there's this third bond, bond 0, which is described as the catch-all interface. It's set up as an active backup bond, with bond 1 as the primary and bond 2 as the backup.
Think of Bond 0 as the main highway for all the network traffic on the Proxmox host. All your VLANs, which let you segment your network, all the bridge interfaces connecting your virtual machines, they all go through Bond 0.
So bond 0 is like the traffic director, making sure everything gets where it needs to go.
And by having Bond 1 as the primary and Bond 2 as the backup, you get automatic failover. If that super fast 10 gigabit path has problems, everything automatically switches over to the slower but still functional 1 gigabit link.
So the system might slow down a bit, but it stays up. That's the priority, right?
Exactly. Service continuity over raw speed when things go wrong.
Now, the creator mentioned that for this seamless failover to work, you need to configure the switches correctly so those VLANs are tagged properly on both those aggregated links.
Right, because the switches need to know that the same network segments are available through both the 10 gigabit and 1 gigabit connections. Otherwise, when the traffic tries to fail over, it's going to get lost. The switch won't know where to send it.
So it's not just about having redundant hardware. It's about making sure everything is configured to work together when a failover happens.
100%. It's that attention to detail that makes all the difference.
Okay, so we've got all this redundancy built in, but what happens when those network paths do fail over? How do you prevent things like network loops, where data gets stuck in a cycle and brings everything down?
That's where Spanning Tree Protocol comes in, STP for short. It's like a traffic cop for your network, making sure data flows smoothly and doesn't get caught in any loops.
So imagine sending a message, and instead of going straight to the recipient, it gets stuck in a loop, going back and forth between switches forever. Not good.
Yeah, that's a recipe for network meltdown. STP steps in and analyzes the network topology, figures out which paths are redundant, and then blocks some of them to prevent loops from forming.
But those blocked paths aren't just sitting there doing nothing, right?
Nope, they're on standby, ready to be activated if the main path fails. STP is constantly monitoring the network, so if it detects a failure, it can quickly re-enable one of those blocked paths and keep the traffic flowing.
Okay, that makes sense. Now, the creator mentioned something about priority and cost settings for those paths. What do those do?
Those settings let you fine-tune how STP works. You can control which paths it prefers under normal conditions and which ones it should use as backups.
So you can make sure traffic takes the most efficient route, and then if something goes down, you have those pre-configured backup paths ready to go.
Exactly. And it's that planning that makes the failover process so smooth. You're not just hoping for the best. You've already defined how you want the network to behave.
So it's not just about redundancy, it's about managed redundancy.
Precisely. And the ultimate test of all this planning, well, the creator actually took down the main core switch to see what would happen.
Don't leave us hanging.
The entire system stayed online. Everything kept working. That's how you know your resilience strategy is solid.
Talk about a stress test. Okay, let's switch gears a bit and talk about firewalls. Now, this is where things get a bit interesting because the creator made some decisions that might seem a little unorthodox.
Yeah, traditionally you'd expect all external traffic to go through a firewall. But in this lab, some of the Proxmox nodes and the virtual machines running on them have direct access to public IPs, bypassing the dedicated pfSense firewalls.
Wait, so they're going straight out to the internet?
For those specific systems, yes. And there's a reason for that. The creator needed those public IPs directly assigned to certain VMs. Routing that traffic through a firewall might have added complexity or introduced latency.
Okay, so it's a trade-off between having a single point of control for security and the specific needs of certain workloads. But what about security risks?
Good point. In this case, the security for those VMs is handled at the operating system level. Each machine has its own software firewall, and the creator has to carefully configure the rules to ensure only the necessary ports are open and everything is locked down tight.
So it's like having a mini firewall on each machine.
Exactly. And it works, but it does mean more responsibility is placed on the administrator to get those configurations right.
It It sounds like there's a potential for things to get complicated, especially if you have a lot of VMs with public IPs.
That's true. It's a decision that requires careful consideration and ongoing diligence to make sure everything stays secure.
Now, this design also reflects some lessons learned from the previous setup, where pfSense was running as virtual appliances within the Proxmox cluster. What were the issues with that approach?
The biggest problem was that the firewalls were dependent on the health of the Proxmox cluster. Remember how we talked about losing quorum and getting locked out?
Yeah, not a fun experience.
Well, if the Proxmox cluster went down, those virtual firewalls could go down with it. Not only would that potentially expose the network, but you could also lose management access to the entire lab.
Talk about a single point of failure. That's not good.
Nope. So the solution was to move to dedicated hardware firewalls, those PF11 and PF12 devices. These are physically separate boxes with their own power supplies and operating systems.
So even if the entire Proxmox cluster crashes and burns, those firewalls are still standing guard.
You got it. They also have their own LAN-side VLANs, which means you can still access them even if the main Proxmox network is down. That's crucial for out-of-band management.
Right, because if everything goes haywire, you need a way to get back in and fix things. Okay, let's talk switches. We've got 2 core switches and 2 access switches. What's the breakdown on those?
For the access layer, there are 2 48-port switches, but they're specialized. One is all SFP plus YO, those high-speed ports for 10 gigabit connections. That's where the Proxmox nodes connect for fast inter-node communication.
So that's for things like live migrations of VMs, where you need to move them between nodes without any downtime, and for shared storage access, right?
Exactly. The other 48-port switch uses standard RJ45 ports, and that's where everything else plugs in. All the management interfaces for the servers, the switches themselves, and any other devices that need a wired connection.
And I heard this switch got filled up pretty quickly.
Yeah, it's a good reminder that you need to think about management and network capacity, too. It's easy to focus on the bandwidth for your main workloads, but all those management interfaces add up.
Definitely something to keep in mind. And what about that 20 gigabit LACP bond we saw on the SFP Plus switch?
That's the connection to the NS, the network-attached storage. Having that much bandwidth dedicated to storage traffic is important for things like backups and moving large files around.
So no bottlenecks when you're backing up all those important VMs or working with large data sets. Makes sense.
Okay, now let's talk storage. The creator has gone with a combination of a NAS, connected via that high-speed link, and local SSDs in each Proxmox node.
So you've got centralized storage on the NAS and then fast local storage for each node. What about Ceph? I know that's a popular option for distributed storage these days.
Ceph was considered but ultimately rejected. The creator decided that for their needs and the scale of the lab, Ceph would have been overkill.
So it's like you don't always need the most complex solution.
Right. Sometimes simpler is better, especially when you factor in the time and effort it takes to manage more complex systems.
Okay, so as we wrap up our deep dive into this awesome home lab, what are some of the key takeaways? What are the big lessons we can all learn from this?
For me, the biggest one is the value of dedicated hardware for critical infrastructure. Yes, virtualized firewalls are convenient, but they create a single point of failure. Having those pfSense appliances as separate boxes makes a huge difference in terms of resilience.
Absolutely. And related to that, you need out-of-band management, IDRA, IPMI, whatever your servers support. You have to be able to access them, even if the main network is down.
Another big takeaway is that spanning tree protocol is still relevant. Yeah, there's been some debate about it, but this lab shows how important it is for managing redundant network paths and preventing loops.
I liked how they used nested network bonds, with both a fast link and a backup link combined into a single interface. That's a clever way to get both speed and redundancy.
And it's a good reminder that we shouldn't be afraid to deviate from those textbook-based practices if it makes sense for our specific situation. Remember those VMs with direct WAN access.
Yeah, sometimes you need to think outside the box.
The other big takeaway is that you don't need a huge budget to build a resilient system. This whole lab was built with careful planning and a focus on eliminating single points of failure. It's achievable.
And the fact that the creator was willing to actually break things, to intentionally take down that core switch and see what would happen, that shows a real commitment to resilience.
So what we've learned today is that building resilient systems isn't just for big companies. With a bit of planning and a focus on those potential points of failure, we can all achieve a level of reliability that would make those big companies jealous.
It's all about those practical lessons, right? Learning from those pain points and constantly improving.
Exactly.
Yeah.
So as you go about your day, Think about your own systems. What are the single points of failure? What's one thing you could do to make your setup more resilient?
Maybe it's adding a backup network connection or setting up out-of-band management.
It doesn't have to be complicated.
Yeah,
Just start thinking about those what-if scenarios, and you'll be well on your way to a more reliable and robust digital life.
great advice. Thanks for joining us for this deep dive.
My pleasure.
Until next time.
Take care.